Hello, everyone. It is a hot day here in Chicago, and so we're going to get through kind of the last part of some fundamentals. And I've been thinking about these last couple of videos. I teach a lot online. I teach a lot in person, creative coding, Max MSP, and there's always there's a kind of like eyes droop factor when we're going through fundamentals here. I've been thinking about this a little bit. The fundamentals are important. They're like, it's a back to the fundamentals approach. I think when we are working with Gen, it's important to understand that we're working a single sample at a time. And also, I think I want to get us to making some sound a little more quickly here. So I'm excited to share that. Just a couple more fundamentals here, and then we're going to turn our attention to LFOs so that we can start controlling time, we can start controlling amplitude, we can start controlling pitch, we can start doing other things like, as I mentioned up here, doing some quantization, so segmenting time in particular ways, segmenting signals for pitch in particular ways, so we can get scales, arpeggios, and so on. So we're going to hop into just first a couple of, I think, pretty important leaps out of fundamentals. So we spent a lot of time looking at the accum object by dividing this by the sample rate. In this case here, we're able to get an oscillator, in particular, what's called a phasor in Gen, a sawtooth wave, and otherwise, in other words, if we wrap that data between 0 and 1, so basically like if it exceeds 0, it's going to flip back to 0, we get this waveform here. But guess what? There's also a phasor operator inside of Gen, which is going to do the exact same thing, right? And so I hope that this is I'm not trying to be purposefully deceitful in terms of withholding information relevant to getting you started. But that is one way that like a lot of functions accumulate, sample rate, and wrap can be bundled into higher level operators. So yeah, we see that this 5 number or integer here is going into accumulate, it's going into phasor. This is then going to correspond with the frequency or the hertz of our sawtooth wave. We're going to be looking at other types of waveforms that can be used for low frequency oscillation. So let's have a look at one of those. This is kind of a similar side by side here. We haven't looked at sine waves, sinusoidal motion yet so far in this series, but we are getting into it, right? So on the left, we have a very similar kind of structure. We have hertz. This time it's parameterized. We can modulate this from the exterior of our Gen patcher. Oops, not like that, but like so. Can change the hertz, and Max is going to put it over there, but we actually want it like here. So we can change this, and that will change the speed of the oscillation, or the frequency rather. Likewise, just like phasor, we divide by sample rate. Here, there's also this phase offset, and this may be important, for instance, if you are doing some kind of like maybe binaural beating effect, and you want the amplitude to be high in the left ear and it to be low in the right ear, or something like this. Here we have phase offset set to going between 0 and 1. So we'll see, I can move this here, and these should be going out of sync. Yeah. So if we go to 0.5, they are 100% out of sync, or 180 degrees off phase. If I go to 25, we'll see that they are offset like so, and so on and so forth. There would be ways to smooth this as well, but we're not really looking at that yet. I just want to illustrate this principle. We wrap this between 0 and 1, and so this is actually really just a phasor again. But if we want to get a sinusoidal motion, we can multiply by 2 pi, 6.28, da 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 da. And then plug that into a sine or a cosine function. Here I use cosine because it seems to map up with this cycle object here, as far as I can tell. So the side-by-side here is that you can do all of this work here. What you get if you're using an oscillator like this, as opposed to just using the cycle operator, is you can do that phase offset there. And yeah, that's, if you don't need that, then you can just use this cycle object or operator, and you can plug your Hertz argument in there. So now we're using sine waveforms. Again, we're talking about low frequency oscillators. For folks who are already familiar with bedrocks of doing audio synthesis, we know that these waveforms are also really useful in audible frequency ranges, which we are going to kind of start to look at right now. Like we see down here, as we turn our attention to the right part of this patch, there's a gen guy here, a gen object that's called VCO type phasor, VCO type S blank. So what is a VCO? A VCO in hardware synthesis is a voltage controlled oscillator. And these are, generally speaking, producing oscillations in the audible range, which is about like 30 hertz to, or 20 hertz maybe sometimes, to 20,000, depending on your ears and people's particular ears. Now, this is called VCO type phasor because, well, there's not really like voltages that are controlling this in the same way that they would in a modular synthesizer. This is a digital system, but the principles are the same. So before we look at the rest of this, what's going on up here, let's click in here and see what is going on. So we have a Hertz operator here, or an input rather. The default is 80. So if nothing is plugged in to number 1, it will be 80, input 1. It's capped. It has a min and a max here. That's like related to approximately the audible frequency sample rate divided by 2. And this is essentially the same thing as our phasor demo here. And so actually I'm just going to put phasor in there, right? Like let's keep this a little simpler. Boom. And we're going to see that works exactly the same. So phasor goes into free verb. I think we looked at this last time. Free verb comes stock with max MSP gen, and that's going to be a free reverb. There may be another meaning to it that I'm unaware of. And basically I'm just mixing. This mix operator here takes, if you have an argument in here, I have an argument of 0.5, it's going to take 2 inputs and mix those 50-50. So we have 50% free verb or reverberated signal and 50% straight. So the other way to talk about this is wet and dry. And then the final part of this circuit is amplitude. So we take that signal and we're going to modulate its amplitude in some ways. And this is a way to create discrete notes, right? Or pulses of some kind. So we have these 2 inputs, and we're going to hear how they sound in a second. Let me save this. Right, so input expects frequency, and input 1 expects frequency. Input 2 expects what? Expects some amplitude. When we're dealing with audible signals, Generally, we want to think about amplitude modulation coming in some range between 0 and 1. And so 0, the amplitude will be totally off, and 1, it will be totally on. Okay, so we know what the VCO is expecting here, amplitude in the right and frequency in the left. So we're going to input some signals in there that are going to control those parameters. Let's start here with amplitude. So what I'm going to do is I'm going to unpatch this from the LFO on the frequency side, so that we have a static pitch. And I'm going to also control manually the amplitude with this signal operator here. And so we hear this change as we go from 0 to 1. And the principle here, you could do a performance like this, right? Where I'm using my hand and my mouse to control this. The principle of using an LFO is that it is a type of modulation. And so often when you hear people speak about using hardware, using modular synthesis, they talk about hands, right? And you have two hands and they can control probably two knobs or buttons or something like that at once, maybe 3 or 4 if you're getting particularly dexterous. But automation frees up a hand. So instead of changing this manually, if I wanted an effect, which is like going between 0 and 1, I can patch this into my low frequency oscillator. And so if we draw our attention to the display here on the right, we'll see that as I change the frequency of this oscillator, the musical effect changes. Now it is increasing, sort of swelling from soft to quiet over a longer period of time. I can continue to change that. I can make that even smaller. I can make it even faster. I can also control the type of waveform using this like an abstraction or a gen operator that I built ahead of time that I'll show in a second. So this is a sawtooth or a phasor waveform. We also have square, which is either going to be on and off. This is also sometimes called a gate signal. We have sine, and I want to draw your attention to the differences between square and these other waveforms in sine. Sine is bipolar, so it will go all the way between -1 and 1, whereas the rest of these are unipolar. They have one pole. They're going between 0 and 1. I think that is important to know. We also have triangle here. That's going to be like a steady ramp between 0 and 1 and back down. This is also where duty cycle can become expressive. So I can morph this into something that is more of a sawtooth or an inverse sawtooth if I move it closer to 0 here. And this is sounding more like a musical envelope, actually, right? There's kind of an attack and then a decay. Great. So if we look inside of here, I'm going to open this up and then we'll return to frequency over here. I'm going to turn this down for a second just to sort of show behind the scenes what is it that's going on inside of this operator. So notice that this is called ccam.lfo.gendsp. I can just put ccam.lfo in here if I have that saved file somewhere. And if I open this project, we'll see that inside code is ccam.lfo right there. So that is something that you can make if you open a gen operator and you save it. Oh, I guess it also shows up here as, wait. Yeah, okay, so this will say .gen.dsp. Here, this is just a generic gen object that has some code in it. Notice that it's not saved as .dsp, .gendsp. So this is sort of more of a shorthand. So sometimes these operators become useful beyond a singular context. You want to reuse them, and an LFO is a good way to do that. As we proceed through this series, I'm going to continue to add to these, and I'll probably change them as I go to, like, something is flagged for me here about this bipolar or unipolar thing that probably deserves revisiting. But that's how this is working here. Very similar to a max abstraction. Okay, so we have amplitude modulation, that is rocking, but we can also automate frequency. So I'm going to take this waveform, which is coming out of an identical LFO. It's going between 0 and 1. That waveform I'm scaling to a frequency value. So this is between movements between 0 and 1 will scale to 220 to 440. This could happen inside of Gen 2. I'm just putting this outside of here because mostly for pedagogical purposes, so it's like clear how the signal is being transformed before it goes into the phasor. Let's hear that. Right, so we have two different waveforms that are controlling amplitude and one that's controlling frequency. We hear the change in frequency. We hear that they're not mapped up entirely, right? There's like some offset here. So we could click to sync these, and that is going to sync these differently, right? They're starting at the same point. The hertz is slightly off. So if I make these both 2 hertz and resync them, both of those operations are happening in the same duration of half a millisecond, 2 hertz. We can change the waveform here as well. And now we're hearing a different operation in the pitch domain. That's sort of all I have to show. I think duty cycle is probably also helpful to show how that works here. So this is only going to work with triangle and square wave, this duty cycle. But we see as we decrease the duty cycle, this on-off or gate-on, gate-off, gate open, gate closed. The on portion decreases. As I increase this, it's going to get closer to just always being on. Maybe a good opportunity for us here to also look under the hood. I started that, but got distracted. So the way that this works, and I think this is maybe also some useful fundamentals for us here. There are 4 waveforms being produced inside of ccam.lfo. And they're being selected by the selector object. So there's only one that can be selected to go out of the output at a time. And that is controlled by the in2. So in2 takes the output of this live.dropdown here, which is a 0 to, it's a 0 base counting system. It goes in the right outlet. 0 becomes 1 so that it can sync up with our selector that expects this first option to be 1. And we have a phasor, which is our sawtooth. And this is actually driving all the 3 other waveforms, which I think is very handy. You could have 4 different sources here. But for instance, if we look at triangle expects basically a phasor to move through that waveform. I'm also, for a similar reason, using the 2 pi and cosine here as well. instead of cycle. I could use cycle here too, and that would be mostly functionally equivalent, except cycle, I could do something like this, right? And plug that in here. Cycle doesn't have a reset to it. And so this is a nice thing about driving all these from a phasor, is that I can reset and synchronize these waveforms if I'm just driving them by the same phasor, and they all stay kind of perfectly in sync that way. The square wave is maybe the most unintuitive for us here. So if you've done square wave or like rectangle wave synthesis in MaxMSP, it looks like this. There is no rect operator here, but it's really easy to make one. We take a phasor value that's going in, just like this one on the left here, and we say if it is less than this duty cycle parameter, then give me a 1, and if not, give me a 0. And that's effectively a gate. The last thing that I want to say about this is this is also kind of a gen particular, is that if we have a parameter here like this, and we give it a name called duty cycle, I can plug that in as the argument for this operator. And effectively, it does the same thing as this functionally, but this looks really nice, right? And I can actually I can write this code a lot quicker that way. Yeah, so that's this. I think what we're going to do next time is actually, we're going to continue to expand how we use ramps in order to have a more nuanced approach to pitch in particular. And we're going to kind of continue to think about LFOs like squares as gates for signals, and not just gates for amplitude, but gates for other kind of data, gates for pitch data as well. And this is a nifty way to make an arpeggiator. So that's that on that. I think we're going to close it out here. If you're stoked on this, give this a follow. Check out the ccam webpage. Follow us on Instagram. We do a lot of different programming across art and technology, but really excited about this particular project here. We're gearing up to offer a set of workshops or maybe a course at Experimental Sound Studio in the probably winter 2027 that uses Gen to program DAISY microcontrollers that are set into some hardware synthesis or hardware synth interfaces that I've designed and taught some workshops with. So stay tuned. That's what we're gearing towards next. I want to start thinking more about musical applications. Notice we're figuring out what some parameters are that we might want to control with our hands, or figuring out what some parameters are that we might want to automate. That is the way forward for this, and we will dip into some more microsoundy things. We're already dealing at the level of microsound, and we will continue to build there. You see a granulator on the menu here. So do stay tuned. Keep cool if it is summer where you are, and talk to you soon.